So thanks, Chair, and for the kind invitation. So today it's really my great honor to share the progress that our team have achieved in the past few years on the development of all solid-state lithium-sulfur batteries. So due to the time limit, so my presentation would be focused on the cathode development. Could you move to the next slide?
You can use the arrow keys. So.
Oh, yeah, okay.
Yeah, perfect.
Yeah, I think I don't have to repeat. Lithium-sulfur battery is one of the most promising energy storage technologies. So this is really evidenced by the quick growth, for the publications and the patent applications from both industry and academia. So such interest, I think, is really driven by the overwhelming advantage of this technology, which is, low cost, high energy, and the use of non-transition metal cathodes. So, but one thing I want to mention, the promise of this technology is not only theoretical. In fact, so practical lithium-sulfur port cells with the cell level energy above 500, even around 600 watt-hour per kg had been demonstrated experimentally. But to really make this technology commercially available, still facing a lot of challenges. So one of the biggest challenge, I think, is the short cycle life. Our next speaker, Kuma, I think will introduce more on these problems. So this is a table summarizes the lithium-sulfur port cell with practical energy over 300 watt-hour per kilogram. From this figure, you can see all the energy is about 300 watt-hour per kilogram, but the cycle life is still limited, which is below 100, even below 50 cycles. There are many factors affecting the cell cycle life, particularly the E to S ratio, meaning the electrolyte amount, the sulfur loading that you use, as well as the C rate that is used for the cell operation. So to quick summarize the for lithium-sulfur battery by using liquid electrolyte, I think the high energy is achievable, but the cycle life is still a limit. This is related to the use of liquid electrolyte, so which cause a lot of issues like lithium polysulfide shuttling, wetting problems of high loading electrode, surface species dissolution and redistribution during the cell operation, as well as the electrolyte depletion and lithium metal corrosion upon the repeated cycles of the battery. There are many efforts, researchers in this area try to address those problems. One straightforward strategy would be switching from liquid to solid-state electrolyte. So in this way, to eliminate all those electrolyte-related issues. But for commercialization of this technology, there are still challenges for all solid-state lithium-sulfur battery, particularly for the cell level energy and the cycle life, are still far beyond the expectation for industry application. So this is a paper, recently published at Nature. So this is a paper published last month, discussing the long-term cycling and fast charging of lithium-sulfur all-solid-state battery. From the numbers, you can see that it is pretty promising. For the cycle life, it could be over 10,000 cycles, and the cell can be charged at over 100 C, even 150 C. But the two things I want to point out regarding this work. First, the anode, instead of lithium metal, the indium is used for the cell cycling. It's not a lithium metal, lithium-sulfur battery. Second, the mass loading of cathode is kind of limited, which is only around 1 milligram per centimeter squared. So my personal opinion would be, without addressing those two issues, it would be very hard to achieve any meaningful energy from the system. So then the question, how to realize the energy goal for all solid-state lithium-sulfur battery. The first consideration definitely is electrolyte.